All right, it's the final piece, IP subnetting part 3. And thankfully, this one's not that difficult at all. It's considered reverse engineering subnets. Up to this point, we've talked about how to subnet based on the number of networks, based on the number of hosts, and now we're going to look at working it backwards, reverse engineering subnets. Now, as I mentioned in the previous video, this is the most common style of subnetting you're going to find in both the real world and in the certification exam. It's essentially a type of subnetting that says, here's the answer, now work backwards. We'll finally wrap up the whole subnetting section by talking about the great exception to the rule, and I'll explain that once we get there. So let's get going with the reverse engineering. Here is a perfect example of reverse engineering a subnet problem. We have a host or a router or a switch on our network, and we look at it and get this IP address information. We see its IP address and we see its subnet mask, and we're faced with the question of, is this IP address even valid? What network range does it belong to? Or, what network is this part of? Is it on the same network as the other hosts that are plugged into the same switch and all that? All of these questions are honing in on reverse engineering, meaning we see the IP address and we see the subnet mask, and we want to know what network range that IP address belongs to. So when you're faced with a problem like this and you're trying to figure it out, we need to work backwards. And in my mind, it's a little easier than the ones we've been doing up till now, like the number of networks and the number of hosts. We don't have to do any of the conversion to binary of those numbers and reserving bits and so on, because we have the answer. This is the answer. Somebody figured out the subnet mask for this host way back when, and in that subnet mask lies the key. We want to know what increment was used when we figured this all out. Meaning this IP address right here belongs to a range, and the only way that we can know the network range is to reverse engineer this, work backwards, and figure out what was the increment. The way we do that is take the lowest subnet masked octet, or the non-255 subnet mask, and break it into binary. So 224 in binary, if we were to lay out our binary chart, 128, 64, 32, 16, 8, 4, 2, 1. 224 is actually 111, 0, 0, 0, 0, 0. Now you can subtract that out and work with it, but after you see these subnet mask values for so long, you start going, oh, well, that's 3 ones. Now, what increment was used with that subnet mask? Well, the lowest network bit, that one, so it is 32. So 32 was the increment that they used when they found these network ranges. So we'll start where they had to start when this subnetting was reverse engineering. And when I say they, I mean the network designers or whoever planned the scheme. So we'll put 192.168.1.0 and just start adding 32. 32, 64, 96, 128. Now we could keep going, but we've passed the IP address. So we can work backwards and find out, oh, this is the network range that they came from, 192.168.1.96 through, 127. Now you can still see it. That's the network range that we're working through. Is this IP address valid? Absolutely not. At least not to be assigned to a host, because that is the last IP address in the range, which makes it the broadcast address, which the only way that you'd be able to figure that out is by doing reverse engineering and seeing the error of assigning that IP address to the host. Let's move on to scenario number 2. Once again, we have an IP address assigned to a PC, 172.16.68.65. We've got the subnet mask listed below, and a default gateway is assigned, 172.16.68.62. IP address down here of the default gateway is 172.16.68.62. Looks good. That's going to be the gateway the computer uses as it goes out. And we see the subnet mask of the default gateway is the same. Everything looks good, and maybe down here is the internet. Now, this scenario might be a typical test question. It might be a scenario in your network environment. Either way, the only way you're going to know if everything is kosher on here is by doing the reverse engineering. So once again, we'll look at the subnet mask, because therein lies the key. We see 255, 255, 255, 240. If we were to break 240 into binary, I should just have a template that I paste up here of my binary numbers, but get used to writing them. 240 in binary is 11110000. So there's our binary value, which means our increment at some point must have been lowest binary value 16. So when the designers of the network put this together, they decided 16 was their increment. Well, let's figure it out and see if we can find what's wrong with this picture or if everything's right. We've got 172.16, 68 zeros where we'll begin and just start adding 16. 16, 32, 48, 64, 80. If we add 16, and we're good. We've passed both those numbers. Now, before we look back at the scenario, you may wonder, well, isn't this a Class B network to start off with? Shouldn't you have started from 172.16.00? Well, I guess you could have, because whoever subnetted this out initially probably started there. But the catch is that when you're incrementing by these values, you're always going to loop back around. Meaning, if I started from 172.16.00 and started adding 16 in that fourth octet, I'd go all the way up to 256 and then go clink, 172.16.1.0. over here, and then we add up all the values to 256 and then go to 2.0. So the point is that you would eventually reach 68.0 by counting by 16. You just take a lot more paperwork to do it. So instead, we can just start from the 0 in the last octet where this network range would have started. And if you look, we passed both of these IP addresses. 65, well, that one shows up right here. And 62, that one shows up right here. So wait a sec, we have a major issue. This PC is assigned an IP address in a different network than its default gateway. It belongs to this network range, 172.16.68.64 through 79. That's where the PC is at. And the router is at the network range above it. That's a big problem. PCs, even if they're plugged into the same switch, like this one is, to the router, if that device is on a different network, it will not be able to reach it. It's not going to know that that device is reachable, because when it compares its subnet mask and ties this all together, the PC goes, wait a sec. My default gateway is not even on my network. It must be somewhere else, meaning I would need a default gateway to reach my default gateway if this is how it would all work out. So this would indicate a communication problem. This would be the breakdown. And now you can see why this is the most common style of subnetting, not only on the exam, because it's very easy to embed something like that into a much bigger question. You know, a scenario might say, oh, you know, PC A here can't access the internet. And there will be a bunch of other scenarios in here of routing tables and protocols and blah, blah, blah to try and throw you off. But really, they're just not on the same network at all. They're not in the same range. Same thing in the real world. You'll need to know if devices are not on the same network, because that's where you need a router between them in order for them to access each other. The way we would fix this is maybe over here the router's connected to another Ethernet network with some PCs, and over here maybe this IP address is assigned, the .62, but this interface would need to have an IP address from the same network range that this host belongs to. Maybe .49 would be valid for this one, so host A can reach it and get through that router to another network. That's what routers do, is bridge networks and connect them together. So at this point, we've seen all three styles of subnetting that you can have. Figured out based on the number of networks, based on the number of hosts, and reverse engineering. I want to mention one more document that I've created for this series, and that is also available on nuggetlab.com. I realize that, many of you may have been going through the examples at the end of every chapter, and a lot of times it is good to just have some practical examples sitting in front of you that you can work off of without needing to go through the whole video to relearn the whole process. Let me show you what I mean, and this will make a little more sense. I've created a document. It's in PDF format. Let me see if I can shrink it down a little bit more. There we go. PDF format right on the website. It is subnetting examples. What I have is in a text document. There are three types of examples that I'll show. one based on the number of networks, one based on the number of hosts, or hosts per network or clients, and then also an example of how to reverse engineer it. So what I've got is, you can see subnetting style 1, subnetting based on the number of networks. And I tried to, as well as I could, walk through my thought process on paper when I'm working through these. Kind of like when I was talking through them in the videos, that's my thoughts. And this is kind of me writing my own thoughts. You know, we've got a service router given this, you must break it into 20 subnets. So step 1, determine subnets and convert to binary. So there it is. Second step, reserve the bits in the mask and find the increment. And we can see the binary tells you how many bits. Your original subnet mask is this. So that's our original subnet mask in all binary. We must convert 5 of them to network bits. So you can see what I did was try and write what my thoughts were in paper. So you can always print this out and refer to it at any time. I did one, subnetting style 1 is an example based on the number of networks with a class C range. The second one is based on the number of networks or subnets with the class B range, because I wanted to give you a feel for each style. Class A is, just like class B, so I didn't really include one of those. We have style number 2 right here based on a number of clients, and then example number 2 is based on a number of clients with a class B address. So I did a class C and a class B for each one of them. And then finally, I have subnetting style 3, which is given an IP address and subnet mask, find the network range. That's the reverse engineering that we just worked through, and that you've got a full example of how that works as well. So I really encourage you to download that, print it out, review it a couple times. It'll kind of solidify everything that we've been talking about in one place. There is one more thing that is in this document, and that's what I want to talk about right now. It is what I would call the great exception. At this point, you've probably seen enough examples to get a feel for how this works, meaning how the process of subnetting works. When I say, we've got 30 hosts per network, and I say our first step is to break that into binary, the reason that I'm doing that, and I'm converting 30 to binary, is because I want to know just how many hosts per network I'm going to need. I think that's the number for 30. I was just doing that while I'm talking, and if that's right, I must be really good, but it's probably wrong. So my thought is that, the reason I have you break that into binary is because I need to know how many bits it takes to get the number 30, because that will tell us how many bits we need to carve out of our subnet mask or save the hosts in order to get an accurate answer. Now, the great exception is kind of related to this whole process and how binary works. Because binary begins counting from 0, these network values may throw off your calculations for the number of networks, and these values may throw off your calculations for the number of hosts. Let me take one of them. Let's say you've been given 200. Here, let me just clear a little room down here. You've been given the IP address 200.0.1.0, and the question says, well, break that into, let's do 16. Break that into 16 networks. Well, when you figure that out in binary, we would say, okay, there's no 128s, no 64s, no 32s, 116, and everything else is 0. So we would say, okay, in that case, it would take 5 bits to get 16 networks. But we can actually get it with 4. 4 bits are what's only required to get 16 networks. And the reason that exception pops in there is because we started counting from 0. Meaning, what's the biggest number you can get with 15? Or, whoops, gave you the answer there. What's the biggest number you can get with 4 bits? Well, if we count them up, let me just write the binary values above. 128, 64, 32, 16, 8, 4, 2, and 1. The biggest number that we can get if we added up 8, 4, 2, and 1, that'd be 12, 14, 15, right? But remember, when we start counting in binary, we start with 0 through 15. So technically, we can get 16 values or 16 numbers with 4 bits, 0 through 15. And that's why anytime you land on one of these significant binary boundaries, like somebody says, well, give me 64 networks, and you put a 1 right there, well, you can actually get 64 with 6 bits rather than the 7 like it looks like it requires. Same thing happens in the host values. says the following host values might throw off your calculations because let's say they said we want networks of 7 hosts per networks. Well, you figure that out and you go, okay, no 128s, no 64s, 32, 16, 8, 4, that leaves us with 3, so 2, 1. That is 7 in binary. Well, when we're working with hosts, it says, well, we need, 3 different values, 3 bits to get the number 7 because 0, hang on, now I'm messing with my own head. This is 1, 2, and 4 right there. So if we add them all up, that would be 0 through 7, if you will, because that's a 7 of total. So it says, well, 8 is the maximum number that you can get with 3 bits. Sorry, I don't know if that makes sense at all, but meaning when you have 3 bits, the biggest number you can get is 8 hosts. Now here's the trouble with the hosts. Anytime we're figuring out these calculations, we always have to subtract 2 because one of those hosts will be the broadcast, one of them will be the network. So when we're looking at this, it shows 0 through 7. Well, that gives us 8 total values that we can have, but if we subtract 2 from 8, we're left with 6. So while we wanted 7 hosts, that was our requirement, give me 7 hosts, this would only give you 6 total values once you subtracted the 2. We'd come up 1 short. So I don't need to get into all the technicalities of why this is the way it is. To play it safe, this is the rule, always subtract 1 when finding the number of networks. Meaning, if the problem or scenario that you're trying to solve says, I want you to figure out 128 networks, well, subtract 1 and figure it out for 127. Or if it's saying, I want you to figure out 30 networks, subtract 1 and figure out for 29. It will never hurt you to do this on whatever calculation you're trying to figure out. It will only help you because it will avoid all of these specialized scenarios. Chances are very slim that somebody's going to come up and say, hey, I want you to figure out how, give me a network range for 63 hosts per network. I mean, that's pretty weird that somebody would be looking for that value. But nonetheless, we can use this rule. Always subtract 1 when finding the number of networks. And to play it safe with the hosts, always add 1 when finding the number of hosts. So if they ask for 63 hosts, because of this rule, you're going to come up 1 short. So just add 1 to the number. Say, well, I'll figure it out for 64. Someone says, I want 20 hosts. Add 1 and figure out for 21. It's going to end up with the same answer if it's not hitting this rule. Or if it's hitting this rule, it may save you a miscalculation. So this is the great exception, and I fully described this in that document that I just showed you, probably a little more concise than the way I've explained it because it's hard when you're trying to show the binary and how that works. But that's the only time the 3 steps will lead you in a little different direction is if one of these values are chosen for the networks or one of these values are chosen for the hosts. With that, I will close the door on IP subnetting. That is the subnetting and the skill that you will need when you are working with anything in the Cisco world, because as a Cisco technician, you have become the network designer. Sure, just about every other certification, Microsoft, Novell, they all talk about subnetting, but you can kind of skate your way through it without really knowing what subnetting's about because you don't usually deal with it in the Microsoft and Novell world. You usually are getting your IP addresses from the Cisco designer that figures out all the networks and divides them up on a map and so on. So it's not as critical to those technologies. In Cisco, you are the network architect, so you have to know how to figure out the subnets and reverse engineer them. So to hit the high points, 3 styles: networks, hosts, and reverse engineering. I would make sure that you are able to figure those out within a decent amount of time if you're planning on taking the certification exam. And the key to these subnetting systems are practice. I know, it's brutal, but that is the only way that this will get down in your own mind. So if you want, you can come up with many different scenarios for your own practice, or go on Google and type in subnetting. Be warned, though, you will see 5,000 different methods of subnetting, and once you try and start mixing many of those methods into your mind, it can just get confusing. So just look online for examples, for some sample questions that you can work through. I hope this